Hi viewers, I am creating these videos to help teachers of maths support their learners in making sense of mathematical concepts and their associated procedures and processes. And today I'm going to look at factorising quadratics, in particular those with a positive coefficient of x squared, and I'll do negative coefficient of x squared in a separate video. And I've got my algebra tiles here to help me. Now, my model for factorization is going to be the same as it was throughout pupils' learning. So when they were learning to factorize numbers, prime factorization of linear expressions. And so if you haven't watched those videos yet, you may want to start with those because some of that will be referenced in this video. Also, obviously, this is designed to come at towards the end of a pupil's learning about factorization and expansion. So if it may well be that pupils need to be familiar with using algebra tiles for expanding and factorizing linear expressions and expanding quadratic expressions in order to get the most out of this. So let's start with a simple quadratic expression. Let's say x squared plus 5x plus 6, and I'm going to build this expression out of my tiles. So there's x squared, 5x, and 6, and my instruction to pupils is going to be the same as it always has been for factorization. Can you build me a rectangle with no gaps and no overlaps that uses these tiles, or that has an area equivalent to the area of these tiles? And I'm going to put in my horizontal and vertical in order to help me with that. So I'm going to build my x squared. Now, the key thing here, obviously, is with the numbers, because my numbers can't line up along either side of this square. So the only thing I can do with these numbers is attach them to a corner of this x square if I'm going to build this rectangle. Okay, because this, I can't put ones along here, they won't line up. I can't put ones along here, I won't line up. And if pupils are familiar with working with algebra tiles, then they'll know that. What that means is if I'm going to create a rectangle out of this and that basically it all comes down to what this rectangle looks like. Is this going to be a 1x6 rectangle, or is it going to be a 2x3 rectangle? And my judgment about that is going to be about, well, which of these, the 2x3 or the 1x6, allows me to fit my x's in the space to create and complete this rectangle? And we can see that in this case, if I have that 6 set up as a 2x3 rectangle, then I can fit my x's. Some of them have to rotate around, but I can fit my x's into there, and now I have a complete rectangle, no gaps, no overlaps. And so my factors, as they always have been, will be what is the length and what is the width of this rectangle. And we can see that the length of this rectangle is x plus 3, and the width of this rectangle is x plus 2. And if I want to sort of support pupils in the journey towards working in the abstract for this, I can draw a picture of something like this. I can say that, this is my rectangle, not a very good one in that case, but this is my rectangle, and I can see that I've built that in ultimately 4 parts, where I've got an x squared part, and importantly, the numerical part has to be corner to corner with the x square, because it can't line up along either of these lengths. And I already know that this x square has a length of x. So my 6 has gone into here. That's where I built my 6 rectangle. And then, it's whether this was a 2x3 rectangle or a 1x6 rectangle. And in this case, it was a 2x3 rectangle. So my 3 has gone there and my 2 has gone there. And we can see in the picture that means I've used 3 x's there and 2 x's there. And that means I've got my 5x altogether. Also, what I might do there is I might say, well, if we sort of look at this in a slightly different way, these algebra tiles or this picture, then what we can see is that some of my x's are vertical and some of them are horizontal. And so what I've in effect done is I've left the x squared alone, but I have switched my 5x into 3 vertical x's and 2 horizontal x's. My 6, however, has stayed together. My 6 ones have stayed together, but I've split my x's so that 3 are vertical and 2 are horizontal. And this, of course, is a fairly standard procedure for factorising quadratics. What I'll now do is say, well, if we look at how that split's happened, or what's the result of that split, is that I could see this as 2 rectangles. I could see it as an x by x plus 3 rectangle, and that's this rectangle along the top here. And then underneath that, I can see a 2 by x plus 3 rectangle. So in total, my area can be considered to be in 2 parts, an x by x plus 3 and a 2 by x plus 3. And then when I combine these together, I, of course, just get an x plus 2 by x plus 3 rectangle. Now, some people prefer to set this up like that. Some people, I know, prefer to set this up using an axis. And I'll talk about that in a little bit more detail in a minute. But one of the things with this axis is that one of the reasons they prefer this is that means that they can have positives and negatives being displayed in a way that's familiar to pupils. Now, there are pros and cons to this, and it's not my particular preferred representation for this, and I'll talk about a bit more about the pros and cons when we look at a quadratic involving negatives. But what I will say about this is if you're going to use this as an axis, then what pupils need to be very familiar with is the idea that positive times positive will give positive, so positive areas will appear here, and also negative times negative will give positive, so positive areas will appear here, with conversely negative areas appearing here because positive times negative, and then negative areas appearing here because positive times negative. It works in a similar way to how this works. And again, it might be useful if pupils have seen something like this beforehand and have recognized these patterns, that positives appear in the upper right and lower left quadrants, negatives appear in the lower right and upper left quadrants when we're multiplying the values that are associated with these axes. So if we were going to do that using an axis, we might set up something like this. These are obviously not part of my area. Those were the lengths and the widths. And again, we're going to have a very similar sort of idea where I'm going to set my 6 up, and it's got to be set up corner to corner with my x squared, and then my x's will fill this space, and that will give me my x plus 3 along my horizontal axis and my x plus 2 along my vertical axis. Okay. Now, one of the reasons I'm not a huge fan of this, although it does have, like I say, it has pros and cons, if I bring this in, is when we start looking at negatives. So if let's take one that's x squared minus 5x plus 6. So what we see here is we've still got my x squared, and now I've got my 6. But where does this 6 go now? Well, if I put it up here, then I'm going to have to fill these gaps with positives, but I've only got negative x's. So actually what I'll need to do is to put these down here. And again, the big question is whether I'm going to put this as a 1 by 6 rectangle or as a 2 by 3 rectangle. And in this case, I can see, well, if I put it as a 1 by 6 rectangle, I'm going to need some negative x's up here to fill this space, and I'm going to need a negative x down here to fill that space. But if I put this as a 2 by 3 rectangle, then I can have 3 negative x's there and 2 negative x's there. Now, of course, the slight issue for me here is that that looks like it's separate. Obviously, if you draw a picture of it, it's not as separate, because you can see now I've got my x squared there, I've got my 6 down here, I've got my negative 3x, and I've got my negative 2x, and I can see that actually, because this is now my axis in effect, that this is a length of x, and this is a length of 3, and then similarly vertically I've got a length of x and a length of negative 2, and I can see that with the tiles here. This is a positive length of x, this is a this is a positive length of x, this is a length of negative 3, and then similarly this is a length of negative 2. So I get my factors x minus 2, x minus 3, but they're all separate, and that's something I'm not particularly keen on with this sort of representation, is they're not all nicely joined up, and these sort of maybe a little bit get in the way, but only really when you're using this physical representation. And you're using the axis with the width there like that. The other reason I'm not a huge fan of this is because obviously when we come to integration, we've got negative area below the x-axis, positive area above the x-axis, so it requires that switch. It's a small thing, but it just sort of influences me away from that. However, what was clear to see there, which is nice, is how my negatives are going to have to fill that space, because it's the only place that I can only have negatives here and there. And if you do that sort of just with a standard rectangle, where you've got your x squared and you've got your 6, it's not as clear, I suppose, that you need negatives filling this space, because positives and negatives could equally fill that space. Obviously, the fact that I've got negative 5x makes it slightly easy to see that it's going to be negatives that fill that space. But then if I have something like x squared plus 5x minus 6, so if I switch that around, then I can see that I put my x squared in and I put my negative 6 in. And in this sort of way of looking at it, just with the horizontal and vertical representing the length and width of a rectangle, it's not immediately necessarily clear that I can't put my 5x's in like that. It's only when you start to examine this, and it requires a bit of knowledge of negative number multiplication here, but it's only when you really start to examine this that you see, well, that would have to be x plus 3 to make these positive, and that would have to be x plus 2 to make these positive, but then these would be positive. So actually that doesn't work. And so actually what has to happen, as we know in this case, is I'm going to have my x squared plus 5x minus 6 like that, and then all 5 of my x's are going to have to be vertical here. And then actually to fill this space, I'm going to need to have a negative x and a positive x. So I'm going to have to create a 0 pair there with an x and a negative x. And this still has obviously the same value as the previous thing. It's still x squared plus 5x minus 6. But it's possibly a little bit harder to see that that's the case, and that that's what I'm going to need to do. Okay, obviously at that point, we have the x plus 6 and the x minus 1. Because this is minus 1, that has the effect of making all of this line negative, which is what I want. Now, if you do that with an axis, then it's potentially slightly easier to see what's going on, because I've got my x squared, I've got my negative 6, but because I'm working in an axis, I know that this negative 6 either has to appear in this quadrant or that quadrant. And again, I know that if I put it in, it can't line up against a single x square, so it can either go like that or like that, or it could potentially be a 2x3 rectangle. But now I can see if I want to put it like that, right, well, I'm going to need to put a negative x here, and I'm going to need to put 6 positive x's here, because the positives has to go here and negative has to go there. And then again, I can do that, and I can make sure that that gives me my 5x, which it does. Okay, now for me, that the sort of drawback of this, like I say, is that these areas end up separate. There's the issue about integration, and also this x squared moves around depending on how you build it. Whereas with the sort of standard length and width, you can always have your x squared starting at the top. The final one I want to look at just very quickly is something like where we've got 2x squared, so we have a coefficient greater than 1 on our x squared. So we can build that in the same way, 2x squared, 7x, and 6. And the key sort of, whether you're building it with an axis or not, I'm not going to here, but whether you're building with an axis or not, the sort of key recognition here that we're looking for in pupils is that if I arrange this as a 2x3 rectangle this way, or as a 1x6 rectangle horizontally, then that's going to require a different number of x's than if I arrange it that way. And that's because this length is now different to that length. So recognition that 2x3 and 3x2 will produce different numbers of x's in this factorization here, and then seeing which one of those is actually going to allow me to fit my x's in. And in this case, it's having it as a 2x3 that way round and rotating. I'm going to cheat slightly here and just copy those in rather than drag. There we are, to complete my rectangle. And again, there I can see I've got my length now of 2x plus 3 and my width of x plus 2. So that is my short video on factorising quadratics and making sense of that using algebra tiles. As always, I'd like to say a big thank you to mathspot.com and its creator Jonathan Hall for the wonderful website that allows me to work with these virtual manipulatives, as well as a huge amount of other material that is useful for teachers of maths. And again, if you've not been to this website before and you've not seen this and used some of its tools, then I strongly suggest you go there, have a look, try some stuff out, because there's some great stuff there. And as always, of course, if you are interested in using manipulatives and visuals to support your learners in making sense of mathematical concepts, then you might want to visit my website. That is visiblemaths.co.uk. And amongst the many things you'll find on there, you will find a link to my book, Visible Maths. And there's the publisher's website is on there. The publisher is Crown House Publishing. And if you click on their link, you can view some sample pages, and if you wish to, if you think it'd be useful, you can place an order. I will be making these videos throughout lockdown and potentially beyond, so if you have a particular maths concept or process or procedure that you feel like you might want modelled using manipulatives or visuals, then please do get in touch. There's a contact form on my website, and I will hope to make it for you. Thank you very much for your kind attention.